So we had a great overview earlier from Dr. Weiss. So we got a sense of gravitational wave astronomy and interferometry as a tool to measure gravitational waves. So now we're going to get a little bit more technical and a little bit more into the details of how these detectors work and what we can detect with them and what's exciting about going forward. So we're going to see again, so something that Dr. Weiss emphasized is that gravitational waves will propagate largely unaffected, and this makes them a really unique probe in astronomy. So we'll see they're very, very weakly interacting. And what this means is that they're particularly tricky to detect, as we learned earlier today. But that also means that they give us this crystal clear signature of whatever dynamical system produced them. So we're going to be able to leverage this to get insights into dense systems that have occluding photons being emitted, and systems that are otherwise impossible for us to observe with traditional telescopes. So we can use this to leverage new insights into a really broad array of physics. So gravitational waves, we're going to see they give us this standard siren measurement. We can directly infer the distance, which is a unique feature to gravitational waves in astronomy, to do things like measure this rate of expansion of the universe, the Hubble constant. And then we also get insight into condensed matter. So these highly, highly dense systems like neutron stars. Gravitational waves can give us insight into how these systems are formed, and particularly through how they tear themselves apart as they collide and merge. So we can also use gravitational waves to get this new insight into general relativity. So gravitational waves allow us to probe this really strongly curved space-time that we heard about earlier. So particularly black holes, and we'll hear from our next talk, very heavy black holes, supermassive black holes like are in the center of our own galaxy. So these are extreme environments that gravitational waves allow us to probe. And it's these stellar mass objects that ground-based detectors can probe at these higher frequencies that have this really strongly curved space-time that's very interesting for us to test GR. And we'll also see, as we've also started to build, we're going to get this census of dead stars, these stellar remnants. And eventually, once we build these next generation detectors and LISA flies, we're going to see this all the way throughout cosmic time. So let's build our intuition. Let's quantify a little bit from what we heard earlier. So we heard that gravitational waves produce this strain, this relative stretching and squeezing of space-time. So we tend to call this lowercase h, or h of t. So this is a function of time that follows this second time derivative of the quadrupole moment. So this is essentially the quantification of what Dr. Rice was saying earlier, of this asymmetric distribution of matter. So this is what we require in order to generate a gravitational wave. So many things can do this. I'm doing this with my arms right now, generating very, very tiny gravitational waves. But there are two other things that I want you to notice about this equation. One is that it's multiplied by a very small number divided by a very, very large number. So as we saw earlier, we expect immediately that this space-time strain, even when this quadrupole moment is absolutely massive, so let's say black holes many tens of times the mass of our own sun, we expect the signal to be very weak. But we should also notice that the strain amplitude scales directly as 1 over the distance. So if we have some intuition for what this time frequency evolution of our signal should be, which will tell us what our strain amplitude be, we can directly infer the distance, which is completely unique to gravitational wave astronomy. And unlike astronomy with telescopes, where you're usually counting flux in some kind of an area, like a photodiode, that's going to scale as 1 over r squared. Here we have gravitational wave strain that scales as 1 over r. So we're going to get this really vast reach into space. So let's come back to this nice diagram that we saw a little bit earlier. So here we have a gravitational wave that's passing into or out of the screen. and it's inducing this relative stretching and squeezing. And if I were to measure the strain, then I'm going to get a time series that looks more or less like this. And it's this orthogonal stretching and squeezing that's going to motivate the shape of my detector. So I'm going to choose 2 orthogonal arms that are going to sample 2 orthogonal degrees of freedom. So let's get a sense of how this works. So we got a basic schematic earlier. Now let's trace the path of the laser light here. So we have this input laser beam. It's split, 50% of the light travels in each direction. It's reflected off a distant mirror. So for the LIGO detectors, this is 4 kilometers. It's recombined at the beam splitter. And if there is no relative change in distance, then we see no interference and no signal at our output port. However, when we start to introduce a gravitational wave, say into the plane of the detector, now we start to see this relative change in phase due to the different travel times of the light in the arms. And it's this interference pattern that we're able to use to directly read out the strain amplitude of gravitational wave signals. And this is how data was taken to generate the plots that Dr. Weiss showed earlier today. And it's not just the LIGO detectors. So as we heard, there is a global network of kilometer scale detectors. So the 3 detectors that I've called out here, so these are the detectors that were most recently active in our latest observing run. So we have the 2 LIGO detectors in the United States. So these are, again, 4 kilometer long arms, one in the desert, fairly close to where I am in the Pacific Northwest, the other down in Louisiana in the swamp with vastly different seismic behavior and ground motion. And then our sister detector, Virgo, is a 3 kilometer detector in Italy. Kagra, as Dr. Weiss mentioned, is a cryogenic underground Japanese detector that's also 3 kilometers long that will, we expect, to join our next observing run. And then LIGO India, which is planned to be built in India. And all of these have the same basic layout, the same orthogonal arm structure, and the same more or less design. And what have we learned so far? So we heard a lot earlier about the 2 biggest discoveries to date, the ones that have caught the most media attention for sure. But I wanted to highlight that we have learned many new things from gravitational waves in just the last 5 years. So what you're seeing here, so on the y-axis, this is solar mass, or times the mass of our own sun. And the x-axis doesn't really have any meaning. It's kind of a schematic to give you a sense of what we know about compact objects. So the astrophysicist in me would call these stellar remnants, these dead stars. So what you're seeing here, these are mostly neutron stars. And all the dots in yellow are neutron star masses that were measured using electromagnetic radiation. And then we have a few of these orange dots here. So these are neutron star masses that were measured with gravitational waves. And then above on this plot, all of these purple dots, so these are black hole masses that are estimated with electromagnetic radiation. So this takes some kind of an X-ray binary system usually. And then each one of these blue dots, so all the gravitational wave systems are triple systems where you have the 2 components that merge to the final object. And each one of these blue dots is the mass of a black hole that's been estimated with gravitational waves. And something you might notice immediately is that gravitational waves now dominate what we know about the masses of stellar mass black holes, and that we've revealed this population that some have found fairly surprising of black holes that are above roughly about 20 solar masses. So before 2015, the largest known stellar mass black hole was less than 20 times the mass of our own sun. And now the majority of stellar mass black holes that we know of and have measured are above this value. And it's gravitational waves that have let us discover this. And I want to call out particularly, so this most massive discovery so far. So this is the first reported definitive detection of an intermediate mass black hole. So this means somewhere between a stellar mass black hole that probably formed from the collapse of a star and these much more massive black holes at the center of galaxies that we'll hear more about in the next talk. So this is a very, very interesting discovery. We're also starting to see through gravitational waves the population of stellar objects or stellar remnants that are in between what we thought of as this mass gap between neutron stars and black holes. So we're really learning a lot already, and something that's difficult to tell from this plot is that we're also measuring this much farther away from Earth than we ever have before. So now I'm going to show you the same plot. So this is mass, again in solar masses, and now we've introduced this axis that's a distance from the Earth. So now here you have these purple dots that are neutron stars. So this is mass versus distance from the Earth. And then black hole masses that are measured electromagnetically. And then each one of these blue dots that you see here, which will again all come in triple systems, are the masses and distances of objects that have been measured with gravitational waves. And you can see that especially for some of these heavier mass systems, we're really probing up to gigaparsecs away that we have these fairly accurate mass measurements. So it's not just that we're probing this entirely new population, it's also extragalactic and really quite far from the Earth. So how do we do this? How do we make this happen with this very simple detector schematic that we've seen? So to give us more of an intuition for how complicated the LIGO detectors are, so we're going to take a tour. So we're going to start by zooming out. So this is above the Hanford detector. You can see this is the mid station here. That's only 2 kilometers away. That's about halfway down the lengths of one of the arms. And the LIGO detectors, so this is 8 kilometers of fully enclosed vacuum system. It's one of the largest vacuum systems in the world, second only, as far as I know, to CERN. And what we're going to do is we're going to follow the beam path. So we're going to start here from our pre-stabilized laser, which is steered into this 3-optic cavity in pink here. So this is the input mode cleaner, which is going to select for this well-behaved Gaussian spatial beam profile. And it's then steered into this power recycling cavity, which Dr. Weiss discussed a bit earlier. So here's our power recycling mirror. So this beam will be reflected and recycled in this 3-optic cavity when it exits the beam splitter, but for now it passes straight to the beam splitter, and we'll see that it splits 50% in each direction, exactly as we saw in our simple Michelson schematic earlier. And now here we're going to zoom out and we're going to see the power of the Fabry-Perot cavities. So Dr. Weiss explained that these are 2 parallel optics, one on each end of the 4-kilometer long arms, and these are going to cycle the light up by a factor of about 300. So we can start from about 180 watts or so as input power, and we'll eventually be able to cycle that up through the signal recycling cavity in the Fabry-Perot cavities to a little less than a megawatt in the arms. And now here we're going to zoom in on one of our output optics. So this is what we call a test mass. This is one of the main mirrors that's cycling the light in the arms. And you can see those very thin fibers are what we use to help reduce the thermal noise for those suspension systems. So now the light has made its way through both of those orthogonal arms. 50% will pass to the power recycling cavity, and then 50% to the signal recycling cavity that serves a similar purpose with a bit more tuning. Finally, to this output mode cleaner bow tie cavity, and then to our photodiode readout. So just to give you a sense of the complexity, it's on the order of about a dozen different distinct optical cavities that all need to be resonating at the same time in order for us to take data. And I'll re-emphasize some of the key technologies that we heard about earlier today. So what you're seeing here in blue, so this is the amplitude of detector noise versus frequency. And there are 3 different frequency regimes that you see here. So Dr. Weiss emphasized the seismic noise at lower frequencies. And what you're seeing here is the active seismic isolation external to the vacuum, which is again a really crucial technology and got us many orders of magnitude in sensitivity relative to prior versions of the interferometer, which did, I would argue, allow us to make that first detection and subsequent detection of black hole systems. So at higher frequencies, so this is where we're dominated by quantum noise, by shot noise. So here our noise is going to scale as 1 over the square root of the power that's circulating in the arms. So not only can we build the Fabry-Perot cavities and the power recycling cavity and signal recycling cavity to cycle up that light, we can also inject more and more light. And so what you're seeing here, so this is our pre-stabilized laser. This is a 1064 nanometer ND YAG laser that will be able to eventually input about 180 watts into the interferometer. And then we're fully quantum limited right now up to seismic noise, but we will eventually come to rest on this thermal noise of our optical coatings. So this actually introduces displacement noise from the thermal coating and behavior of the very thin coating that we use to reflect the light. That's actually going to start to wiggle the mirrors around just a very little bit. So this happens at roughly about 100 hertz, and I'm going to say more about what we're doing to combat this for future detectors. So I wanted to highlight coating noise. So this is really a fundamental material science problem, again, weaving in this wonderful interdisciplinarity of this field. So in order to sense further out into space, what we most need to combat in our most sensitive frequency range, at least for the ground-based detectors, is indeed this very, very small atom level motion on our optical coatings themselves. So what does all this technology buy us? So we're going to see to scale here the relative displacement measurement that the interferometers can make. So we start by orbiting around the electron outside of a hydrogen atom. We're going to zoom all the way down to the proton. And this animation was made, it's worth noting, in 2015. So we actually do about a factor of 2 better now. But this is to scale the sensitivity of the LIGO detectors in making this relative displacement measurement. So 10,000 times smaller than the width of a proton. And as you might imagine, it doesn't take too much to shake the interferometers around just a little bit. And someone asked a really good question earlier about trying to take data continuously. And the key word there, I would say, is try. We do try to take data consistently, but we have a lot of essentially issues in maintaining the light resonance in all those different optical cavities that we saw. And what you're seeing here is an image of the wind speed around the world, which is one thing that we tend to struggle with in terms of keeping the interferometer in resonance. So ocean waves, winds, earthquakes, other sources of ground motion like trucks and trains, these can all cause us to lose light resonance, which means we can't take data. So that ends up giving us roughly about the same duty cycle as a telescope that would have to worry about day versus night, but we have to worry about ground motion and distant earthquakes. And as you might imagine, even when we can take data, sometimes we do get some non-stationarity in our data. So what you're seeing here, so this is real LIGO strain data. This is for our Hanford detector. And this is a 10-minute span that you're seeing here. And this is frequency versus time. So here I'm also showing a microphone that's near the input optics that we just toured. And you might notice this very distinct Doppler pattern, this very strong frequency harmonics that are shifting downward. This is actually a Chinook helicopter that's flying over the control room. And you can actually see the point of closest approach here in this Doppler shift pattern. So we do have quite a lot of non-stationarity. So this is actually only 10 minutes or so away from this intermediate mass black hole detection that I just discussed earlier. So transient characterization and understanding the transient nature of our data is a very important task. So we do have some sophisticated algorithms that allow us to do this. So one of these is called Gravity Spy, and I'd highly recommend looking into this for those of you who also are interested in transient characterization. So you can read more on gravityspy.org. But I want to close by saying just a little bit about the future and putting things into some context from what we heard earlier. So Dr. Weiss mentioned that over the course of these 3 observing runs, so starting in 2015 when we were seeing about 1 event a month, up to our most recent observing run, 03, where we were seeing more than 1 event per week, it's really a very subtle change in our sensitivity. So here's our strain noise versus frequency again, and it's these very, very small shifts that we're seeing in the amplitude of this noise that are giving us a little bit more reach and distance, which is then getting cubed. And now we're really starting to see this exponential growth of events. And to put an even finer point on it, so here is the sensitivity curve where we just ended this last observing run, roughly about 1 signal per week. We expect to see up to 1 signal per day, and this is a gold-plated significant detection per day in our next observing run, which should start about the middle of next year in 2022. And I think I will leave you here. So with what else we might detect with current ground-based detectors. So here we see a coverage of our parameter space with templates. So this is some accurate prediction from general relativity in terms of what the signal might look like. So here we've got sources we've already detected. So binary neutron stars, binary black holes, our first intermediate mass black hole, and some of these more exotic binary systems like eccentric systems. Also core-collapsed supernovae, which we mentioned earlier, would be a real treasure trove of discovery. And then we also have these longer duration signals that we are actively looking for with LIGO-Virgo and Kagra data. So the stochastic background that Dr. Weiss mentioned, and then of course these continuous waves from spinning neutron stars that should give us that additional insight into this extremely dense matter. And maybe the most exciting of all is, of course, something we don't expect. So with that, I'd be very happy to take any questions.
Thank you, Jess. That was an excellent talk.